In the previous video, we have seen how to detect infeasibility of the global AllDifferent constraint, but we still have to decide how to implement the filtering, that is the removal of all the inconsistent values of the AllDifferent constraint to achieve what we call the domain consistency. So a first idea that you might come with, since the feasibility check is performed with the maximum matching, is you may say, okay, let's try to enumerate all the maximum matching in my graph of variable value, the bipartite variable value graph, and we take the union of all the edges, okay, and if we detect that one of the edges does not belong to the final collection, so does not belong to any maximum matching, then we can simply delete this edge and so remove the corresponding value from the variable. Is this a practical approach? Clearly not, because if you have n variables and each variable has a domain that is as large as n as well, then you will end up with factorial n number of matching to consider. That's even worse than exponential in that case. And so you clearly do not want to implement this filtering algorithm inside the propagator of the AllDifferent constraint, although that would be a valid algorithm. So fortunately, there is a French mathematician, Claude Birch, that invented a theorem that can save us a lot of time. This theorem tells us that if an edge belongs to some maximum matching, it belongs to some maximum matching if and only if, for an arbitrary maximum matching M, anyone, okay, you take a maximum matching M, anyone, you consider an edge and you say, does this edge belongs to the maximum matching or not? And the answer will be yes if there is an even alternating path that starts at an M3 vertex, okay, or there is an alternating path that is of even number of edges. That's the second case. If one of the two cases are true involving this edge, this candidate edge E, then you know that this edge can belong to some maximum matching, and as a consequence, it should not be removed from the bipartite graph. Let's reuse this very important theorem, okay? It will become a little bit more clear when I will introduce the visual examples. But this theorem is very important because basically it will boils down in terms of filtering algorithm to detect cycles in a directed graph. Okay, this is what we will see now. But that's already the main idea. So the case one of this theorem. Let's start from a maximum matching that is represented in blue. That's a maximum matching in my bipartite graph. And the first case of the theorem tells me that an edge belongs to some maximum matching if for this matching, it belongs to an even alternating path that starts at an M3 vertex. Okay, it's a maximum matching in my variable value graph. We know that the constraint is consistent, so the two free nodes, M3 nodes, are necessarily on the value side there. Okay, so I try to discover if there is an alternating path, okay, that is of even number, so 1, 2, so it will also end up in the value side, okay, that is alternating. Let's try to see one example, okay, I can find at least one there, okay. What you can see is that this one is of even number, it has a cardinality of 2, and if you flip the status of the edges along that path, then you still have a maximum matching. It means that this edge belongs to some maximum matching. Okay? It doesn't tell you which one, but you know that it belongs to at least one maximum matching. The second case of the theorem is this one, is an edge belongs to some maximum matching if starting from M, it belongs to an even alternating cycle. So let's try to discover an even alternating cycle to illustrate the consequence of this theorem. So that's an even alternating cycle, right? And the cycles, since it's a bipartite graph, there will always be of even numbers in this case. Again, along this cycle, you can flip the status of the edge and you still have something that is valid, that's still a maximum matching. So this one would enter into the matching, this one not, this one would enter into the matching, and this one not. Okay? And you still have a maximum matching. The consequence of that is that these two edges also belong to some maximum matching. Okay, they also belong to some maximum matching M. And so they should not be filtered by the filtering algorithm. It's just one example, right? But you can convince yourself that it's the case for all the possible examples in this illustration. So the filtering algorithm will be this one. If an edge, okay, an edge E belongs to some maximum matching, if it belongs to a specific particular maximum matching, that's the first case, okay? Or it belongs to an even alternating path that starts at an M3 vertex, or it belongs to an even alternating cycle. And the good news is that we can treat the two cases of Birch's theorem as one by transforming the graph first. Let's see this very interesting transformation that was invented by Jean-Charles Régent. The transformation is the following. We will add what we call a dummy node, this one, okay? This one does not correspond to a variable or value, it's just a node that is there to help us in our implementation. So it's a dummy node. Then we will orient the edges. We will orient the edge that belong to the matching from the left to the right, okay, such as this one, okay, from the value to the variable direction. And the black edges that do not belong to the maximum matching, we will orient them from the left to the right. Okay, so for instance, this edge 4, 3, you see that it was oriented like this. Okay, like this. And once I have done this, I also need to add edges from the dummy node here. Okay, I add an edge from dummy node to all the value node if the value node is matched in the maximum matching. So this one is matched, so I will add an edge in that direction. But for the free vertices, like these two ones, the free node vertices, I will add the edge in the other direction. Okay, I will add them in that direction. And once I have done that, the first case of the Birch's theorem is exactly, can be rephrased using this transform graph as follows. Every directed cycle that contains an arc from an M3, an arc from a vertex that is matched to an M3 vertex corresponds to an even alternating path. Okay, so, and that's the case of this orange cycle that you can see there. Okay, so that's a cycle, okay, and it corresponds to the even alternating path, okay, because this one is matched, this one is not matched. And to close the cycle, since we have introduced these edges in that direction and introduced these edges in that direction, you can close this cycle, right? What is important to notice there is that you can detect this first case of Birch's theorem by detecting the cycles, and these cycles will have the property that they will go through the dummy nodes that you have introduced. Now the second case of Birch's theorem will not use the dummy node, okay? It corresponds to the even alternating cycle, and you can visualize an example here, okay? This one, this one, this one is an alternating cycle, right? Here, and you see that we are not going through the dummy node, okay? But again, in this transform graph, it corresponds to a directed cycle in the graph. And so we can merge the two cases with just one detection algorithm to decide if an edge belongs or not to some maximum matching. And that's the new theorem using the transform graph. An edge belongs to some maximum matching if either E belongs to the initial matching or E belongs to some directed cycle in the transform graph of M, okay? And so this is exactly what we have shown before. You compute the transform graph, you detect the cycles, okay? And once you have detected the cycles, you know that the edges that belong to the cycles also at least belong to some maximum matching. The detection of the cycles, of the directed cycles in a directed graph, you can do that, you can compute them all using what we call the strongly connected components. And they are very efficient algorithm to do that. Linear in the number of edges, it's the algorithm of Kozaraju or the algorithm of Tarjan. So let's wrap up a little bit the filtering algorithm of Jean-Charles Régin introduced in 94 for the AllDifferent constraint. First, you compute the maximum matching that covers the variables in the variable value graph. Then you will remove all the edges XA that does not belong to some maximum matching. And what we mean by does not belong to some maximum matching, since we have used the transform graph and the Bayes theorem, it means that we can safely remove A from the domain of X if this edge does not belong to the maximum matching, or A and X, this edge, belongs to two different strongly connected components in the transform graph. If that's the case, it means that this edge does not belong to a valid alternating cycles. According to the Bayes theorem, this edge does not belong to some maximum matching, and consequently, we can remove it from the domain. We can remove A from the domain of X. So I have represented here a color code for all the strongly connected components. So for instance, these four ones, you see that they have the same color because they belong to the same strongly connected component. Okay? And so we can remove all the black arcs that connect two different strongly connected components if this black arc does also not belong to the maximum matching. Let's see which one they are. Okay. For instance, here, no, I don't have the example there. So let's summarize. I have illustrated there the ones that need to be removed. So the first step, we build the variable value graph. Then we compute the maximum matching to detect if the AllDifferent constraint is consistent. Once it's done, we do the transform graph. We do the directed graph. Then we compute the strongly connected components. And once we have done that, we identified all the edges that link two nodes that belong to different strongly connected components. You can see, for instance, that this edge that is represented with a dashed line is connecting two nodes that belongs to different strongly connected components, and therefore it can be removed. Okay, 3 can be removed from this value can be removed from the domain of that variable because there is no maximum matching that would involve this edge. Okay, that's the same for this one, and all the dashed edges that I have represented there. That's the algorithm for filtering the AllDifferent constraint and achieving domain consistency for that constraint.